Okay, models, laws, theories. If you had to summarize the one thing from the day that I rented, what would it be, Adam?
Second test made me like a truck.
No, not that one. Not that one, but that's a good one to remember. Theories do not become laws. Using the phrase, it's just a theory, is wrong. Okay, because theories can be very good. Great joke. What's the one? Thank you, Adam. All right, so moving along here. Science is more than just a collection of facts and observations. Models, laws, theories, and evidence all play an important role in understanding the nature of science. A scientific model is, that sounds like a definition. A scientific model is, and now my Word document just is not responding. A scientific model is a conceptual representation, an idea in your head that stands for and helps explain other things. So a model is a way to help explain other things. Kaylee, you're not following along. You're highlighting your hair. Travis is unique. Don't try to be like it. A scientific model is a conceptual representation, an idea in your head that stands for and helps explain other things. It can be physical, for example.
Yes.
The globe, physical model, or it can be imagined in your brain, or mathematical. Or an example of imaginary one would be the Bohr model, right? Because we don't actually see that. It's a way of describing the Bohr model, with the electrons rotating around. Or it could be a mathematical, like numbers and formulas. In science, we develop models that have explanatory and predictive powers. In other words, they explain things and they predict. The globe is a model that predicts that if you go all the way around the world on a boat, you're not going to fall off. If suddenly we discovered that people were falling off the edge of the Earth, we might change our model from a globe to a flat disk. Not true, by the way. If our model predicts our observations, we accept the model as a valid description of our world. However, if our model encounters discrepant events, there's a word you've probably never seen before. Travis, you're not listening. You're highlighting. A discrepant event. A discrepant event is an event that you didn't expect to happen. For example, if you wake up tomorrow morning and the sun does not come up in the east, that's a discrepant event. That's unusual. If people start falling off the edge of the world, that's a discrepant event. It doesn't match what should be happening. Okay? A good example of a scientific model is the model of the solar system. I'm going to pause. Okay. A good example of a scientific model is the model of the solar system. At one time, it was thought that the sun revolved around the Earth, and this geocentric model of the universe was considered to be a true representation for many centuries. Geocentric, with the Earth at the center. They originally thought the Earth was at the center of the solar system, the universe, in fact, right? As you look out during the daytime, what does the sun do? It goes across the sky, right? The moon goes across the sky. At nighttime, the stars go across the sky. It looks like everything is rotating around us. Humans tend to be very self-centered. Oh, I'm the center of the universe, right? Here's the tip, you're not. Okay? Is the sun the center of our universe?
Center of a galaxy.
It's the center. It's the center of our little solar system, our little corner of the world. Yeah. The universe. Okay, so this was considered to be true. The model encountered a discrepant event when the retrograde motion of the planets did not exactly fit the epicycles of the geocentric model. Suddenly, I stopped speaking English. Yeah, let me explain. Retrograde motion is when you go. See that? If I walk like this all the time, it'd be kind of funny, wouldn't it? Especially if I do that kind of walk. The retrograde motion is when I go backwards every once in a while. So, planets, do you know the difference between planets and stars when you look at them in the night sky? What's the difference? Oh, you don't know? Didn't you say yes?
Yeah.
Oh, okay, just check. Just check. What do the planets look like? They tend to be a little bit bigger, they tend to be a little bit brighter, right? They don't flicker, and they move weird. Have you seen, everyone knows what the Big Dipper looks like, right?
Yeah.
Okay, so like it's kind of like that, right? Does it look like that everywhere on the sky? The answer is yes. The stars all move sort of together, the same, right? But the planets move weird. They kind of move on their own, and they have this kind of little backwards loop-de-loop thing known as retrograde motion. In fact, the word planets comes from the Greek planetos, which means wanderers. I think it's Greek. Don't quote me. I'll be laughing. Okay? I'm just making this up. I know this stuff, right? The word planets means wanderers because they wander through the constellations. Okay? So, the geocentric model, Kaylee, the Earth is at the center, encounters a discrepant event when those planets do this retrograde thing. It doesn't make sense. Why do planets do this? Okay, so we've got a discrepant event, we've got something that doesn't match the model. The new model, the Copernican sun-centered model, named the Copernican model because it's named after Copernicus. He said, you know what, you guys, put the sun at the center, and then what does it look like? Well, all the planets are now rotating in a, I mean, I didn't draw very well, but it's all nice and simple. No more retrograde motion. Copernicus simplified it. And once they sort of, spent 100 years debating it, okay, then that works good. The new model, the Copernican sun-centered model, provides a simple explanation of the movement of the planets, and it predicted the phases on Venus. So what I mean by that is, when you look at the moon at nighttime, quite often it's like a quarter moon, half moon, three-quarter moon, full moon. You guys know what that means, right? Okay. Copernicus said, you know what? With my model, the same thing's going to happen with Venus. Of course, they didn't have telescopes back then to prove it. A couple hundred years later, along came Galileo with his fancy new telescope that he just invented. He looks at Venus, and what do you know? Phases on Venus. So, Copernicus's model made a prediction that wasn't able to be verified for like 100 or 200 years. So, it's pretty good. Noah's got a question or just scratching? Okay. Years later, the invention of the telescope permitted more capable. Observations can be used to test models, both externally or by thought experiments, as we can rethink and apply our model to new and sometimes discrepant situations. Our observations can lead us to identify regularities and patterns in nature. See how I emphasize that? Why did I emphasize that? You will find, if you attend a university class, that professors will do that sort of thing, but they're not going to say, you should highlight that, that's important. But they're saying that by doing it by using that emphasis. Right? So where is that here? You're following along, right? We call these regularities and patterns scientific laws. A law is a regularity or pattern. For example, a simple scientific law would be what goes up must come down. We can also deduce laws given a certain set of conditions. For example, if light is a wave, we can geometrically show that the ratio of the sines of the angles of incidence and the refraction is a constant. Again, going into non-English, making weird noises kind of stuff, right? It's called Snell's law. We often represent laws as mathematical relationships. Snell's law, Ohm's law, Charles' law, Newton's laws. All of these laws make predictions, sometimes mathematical. Okay? Snell's law is about the wave property of light. Tells you, you know how when you put a pencil in water and it refracts, it bends? That's Snell's law. Applied there. Contrary to popular belief, laws are not absolute but are often constrained to certain conditions. In other words, laws aren't always true. Ohm's law is valid only for some materials, and our pressure laws are constrained by temperature. Even Newton's laws are valid only in inertial frames of reference. Here on Earth, what goes up must come down. Take this to the space station, what goes up never comes down. Keeps on going. Right? So laws are not always true. Now, the last one here. Scientific theories. This is the big one that I ranted about. Scientific theories form explanatory systems for phenomena and the corresponding laws and may include presuppositions, models, facts, and laws. In other words, scientific theories explain how things work. Scientific theories explain how things work. It's not there.
Oh.
Scientific theories explain how things work.
Okay.
They might include presuppositions, which is a fancy word for assumptions. They might include models, they might include facts, they might include laws. They are sort of the textbook of how things work. For example, Einstein's theories presuppose or assume that the speed of light is constant in all frames of reference. In Einstein's world, Newton's laws, such as F equals ma, hold only for objects that are moving much more slowly than the speed of light. So, out of this so far, we've got models, our physical descriptions or imaginary descriptions of something. We've got laws, our regularities and patterns, and we got theories, our scientific theories. What did they say? Yeah, well, what did I say? I put it in English. Explain how things work. You got your three definitions there. Jade, you should stay. This is pretty important. I know you got to go, but how are you going to miss all this? Okay, next paragraph, and here's where the ranting part came in. We must be very careful how we use the term theory. In everyday usage, the word theory often refers to an idea that is not proven. In fact, that is, starts with an R, rubbish, thank you. It's partially true that some theories, like many cosmological theories, are speculative ideas and based on little evidence. Additionally, children often hold simple or naive theories about why things float or why the sky is blue. Hypotheses or proposed solutions are also often speculative, and we often seek to build support for them through predictions and observations. However, other theories, like theories of radiation, metabolism, chemical bonding, have considerable evidential support. There's a lot of evidence backing them up. It is impossible to prove our theories for every possible case, but robust theories, oh, I hate when that happens. Robust theories explain a great deal, and we sometimes literally bet our lives on it. Okay? I would like you to, at the bottom of the page, and you probably wrote this down somewhere else. Do you have this? Oh, I hate it when it does this. No, I don't. Go away. Did you write this down the other day? Speculative. Robust. Two words you need to know. A speculative theory is one that what? Go ahead. Yeah, go ahead. I'm sure you got it. You're afraid that you don't know. Go ahead, give it a try. Come on, deep breath.
It's like,
Does it have a lot of evidence or not so much evidence? Just a little bit, not so much. Is it generally accepted, Christine? No, in fact, there's very few people that believe it, right? Speculative means it's still in its infancy. It's still being determined, still being worked out. Speculative. A robust theory is one that's been around a long time, knows what it's doing, kind of like me, has a lot of evidence, generally accepted as fact, yeah, just like me. I'm robust. Could speculative theories be discarded, Josh? Yeah, they might say, you know what, this really doesn't explain what's going on. We're going to get rid of this one. Right? Okay. Now, last little sentence there, and I really wish it was on the next page. In science education, we often use early models of theories that are adequate for a less sophisticated understanding of a scientific concept. For example, Bohr's model of the atom turns out to be, well, not really true. Big lie. You don't know how many times he lied to you. In science education, we often use early models of theories that are adequate for a less sophisticated understanding of a scientific concept. For example, Bohr's model of the atom explains all the phenomena one might examine in an introductory chemistry program. More progressive theories require a more extensive background. In other words, to quote Jack Nicholson, you can't handle the truth. Maybe you've seen that movie. What's it called? Few Good Men, Tom Cruise. Anyways, okay? So yeah, you're taught the Bohr model because it explains the basics, right? But as you get more and more down the road in chemistry, you're going to learn that the Bohr model doesn't quite cut it, and there's different sort of ways to describe things. Another good example is when you first learned about subtraction. You were probably told, or maybe it was always done, the bigger number was always first, right? 7 minus 2, 9 minus 7. How come? Because you couldn't do it the other way. And then about grade, I don't know, 7 or so, you learned about integers, and then you could do 2 minus 7, right? You probably all know that you can't divide by 0, right? Okay, maybe not. You probably all know that you can't take the square root of a negative number, right? Well, that's not entirely true. There's lots of those little things in math where they don't quite give you all the truth. There's a few things in real life too. I'll let you figure those ones out for yourselves. There's one around Christmas time that I'm talking about. Let's move on. While it's important that our understanding of the science, nature of science, hang in there, you guys. While it's important that our understanding of the nature of science is embedded in the context that the world is rational and can be understood, we never really know if we've achieved the most rational explanation or the best one. In science, the truth is elusive, but our beliefs must extend far beyond individual opinions. In science, we insist on an evidential argument. In other words, we insist that there be some evidence. We can't just go with our opinion. Go away. One of the main questions that scientists are concerned with is the relationship between theory and evidence. It's not unusual in science education to make a knowledge claim in the form of "I know that." For example, while discussing health with your doctor, she might say that lowering cholesterol level lowers one risk of heart disease. Now, if the doctor says that to you and you don't know anything about heart disease or cholesterol, you might not know what they're saying. So they might say something like, you should cut down on your meat. Eat less eggs. Right? The doctor has to tailor the message to the level of the student or the level of the patient. And the same thing here. I have to sort of translate some of this highfalutin stuff, C word, this is coaching call it, into your words so you can understand. Okay? Blah, 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 blah. We don't need that. Blah, 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 blah. Aha. Find this one right here. Don't be going to the bathroom now. You guys got to stay. You got to listen. Go to the bathroom before class. Go. Not now. You'll get a chance. Right here. I know you're just wanting to go for a walk because you're getting bored. I get it. Hang with me. Go before class, Jay. Seriously, man. Okay? A good theory is accurate. The predictions the theory makes closely match the observations made to support the theory. However, accuracy is not the only characteristic of a good theory. When two theories are equally accurate, the better theory is often the simpler one. Well done, you guys. Some of you picked up on that.
Oh.
What did I do? I said a sentence with a little bit of emphasis, and then I paused. And some of you recognize right away. Some of you recognize that, oh, I'm supposed to do something because he's pausing. It's okay. That's one of my jobs, is to teach you how to sit in the class and listen. I'll go back again. When two theories are equally accurate, the better theory is often the simpler one. The Copernican model of the solar system was no more accurate than the Ptolemaic model, with a series of epicycles to account for the motion of the planets. In other words, they still described exactly the same thing. In the face of equally accurate models, Copernicus' theory simplified the model of the solar system tremendously. It became just a bunch of circles. It made things a whole lot simpler. When you got two explanations, one really complicated, one really simple, which did you pick? Simple. There's a name for that. I'm going to tell you what that is. Furthermore, a good scientific theory has explanatory powers that cover a broad scope. In other words, they explain a lot of things. It explains a lot, even phenomena it was not intended to explain. The scope of a good theory also extends to bold predictions. Often these predictions, such as Einstein's prediction that light would bend near large bodies, are not confirmed until years later. In fact, just recently, Einstein had predicted a thing known as gravitational waves. It was just last year that they actually observed them. It might have been this year, I'm not sure. It wasn't like, it's in the last year or so, right? So his theory can be considered to be really good. No theory, just a theory, but it explains things. Okay. Yak. You've got another hand out there, right? I'm not going to read that one. This one is written at the level that grade 11 students should be able to handle. Okay? There might be a few big words in there. There are a few questions as well. on the backside that will help you sort of focus your thoughts. I'm going to take about a 2-minute break because I need a break too. If you need to go to the bathroom or check your phone because mom's been texting you for the last half an hour, okay? If mom has been texting you for the last half hour, you should answer, Mr. Bennett is teaching, I can't answer. Okay? In about 2.5 minutes, I'm going to come back and I'm going to talk about clever hands. Okay? And then I'm going to give you some time to work on the lab. Simony. Okay? Not all explanations for a knowledge claim are created equal. Some explanations involve more details and make more assumptions than others. In other words, they are more complicated. Assume you are confronted by 2 explanations for the same phenomenon. Both of them seem equally plausible. What does the word plausible mean? I know, you know? Possible or likely or makes sense, I guess you could say. Which one would you select? The one that involved numerous assumptions and details or the one that involved fewer assumptions and details? Usually, people would pick the fewer, the simplest, right? Usually, simpler is best. If common sense tells you to select the explanation that makes the fewest assumptions, remember that assumptions also require explanations, then you already have a good understanding of the law of parsimony. Here's an old but excellent example of the law of parsimony. In the early 1900s, Mr. Wilhelm von Osten, a retired mathematics teacher, owned a remarkable horse named Clever Hans. Hans became world famous because he could apparently solve mathematical problems that involved decimals, fractions, tell time, read, among other remarkable abilities. He was smarter than the average bear, as the Yogi Bear cartoons used to go. Pretty smart horse. For example, someone, his trainer as well as strangers, might ask Hans what 7 divided by 4 equals. Who wants to try it? What's 7 divided by 4 without a calculator?
2.3. 1.8.
Thank you.
I said 1.89.
Did you?
Yeah,
Hans, the horse, would tap the answer out with his hoof and receive a treat when he was correct, which was well over 90% of the time. The horse was right over 90% of the time. A committee that included the noted German psychologist Karl Stumpf was appointed by the German government to study the phenomenal horse and prove his so-called abilities were nothing but a hoax. The committee completed their task and reported that although they were unable to prove that Hans was receiving intentional cues, they remained unconvinced that he was able to solve such mathematical problems and complete the remarkable feats by using his cognitive process. In other words, his brain. They couldn't prove that the horse was cheating, but they were pretty sure he was. Because they couldn't figure it out. Horses can't do math. Horses are smart. They don't do math. Stumpf's assistant, Oskar Funst, decided to continue investigating the phenomenal horse. Funst conducted several experiments and concluded that when Hans could see the person asking the questions, he was able to supply the correct answer. So if the horse could see whoever was asking the question, the horse was right. If Hans could not see the person asking the question, then his performance fell to near 0 levels, almost always wrong. Funst was faced with 2 alternative explanations for the horse's abilities. Hans understood the questions and was able to use cognitive processes, but only when he was able to see the questioner. That's an explanation. That's a theory. Or the person asking the question was somehow inadvertently cueing the horse. You know what I mean by cueing? Giving them a signal when to stop tapping at the appropriate moment. Applying the law of parsimony, which says the simplest one is likely correct. Which one of those 2 is the simplest? The first one? The second one, that the person was giving the horse a signal. Right? The other one is that horses are really smart. So theory, not very good. Applying the law of parsimony, Funks chose the latter explanation and persisted in his investigations. He finally determined that almost everyone who asked questions of Hans made a minute upward movement of their head when the correct answer was reached. When the answer was correct, the person's head went like this, and their eyebrows went up like this, and their eyes got really big. It wasn't quite that obvious. And the horse was pretty smart and recognized that when the person does that, I should stop and I get a sugar cube or an apple or something nice, right? Pretty smart horse. Doing math? No, just reading body language. Students do it all the time. I ask questions, then I stop and I get them notes. This, and what does that usually mean? It means try again, right? And what if I go like this? You're right. But what if I do nothing? What do students do? Almost always give me the other one. If I say true or false, blah, 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 then I go, people will go true, no false, no true, false. They try to do both, right? You see that all the time? Yep. Okay? I try not to give body language to make you think. But that's what the horse is doing. If you apply the law of parsimony as you evaluate knowledge claims, you're well on your way to becoming a good psychological tutor. Do you understand the law of parsimony? If you had to summarize it in about like 8 words, what would it be? The simplest, what, Connor? Simplest explanation or simplest solution is usually right. Okay, I'm going to stop talking. You've got some time. I regret there's not a lot of materials. There are some in the back that you can use. If you've submitted the lab, I strongly suggest you read the middle sheet, answer some questions. If you've done that, if you got some math or some English or something else you need to work on, great. If you need help with the lab, this is your time. This is it. Get her done. Tomorrow I'm doing vectors, ruler and a protractor.